Hey, and welcome back. Part 3 of 6.2. All right, this is where it's going to get lots of fun. We've got, looks like about 3 or 4 examples, and you get your next set of homework. So let's get started. So on this first one, we're going to do some trig identities in order to help us facilitate our substitution. So it's like substituting twice, but using really our trig identities. So this first one here in part A, this one right here is telling me integral of 1 over cosine squared of 2x. Again, if I look at my integral tables, I don't have a cosine squared 2x or 1 over cosine squared 2x. What do I have? Well, so now I have to go back to, well, what is really 1 over cosine? Well, secant. So 1 over cosine squared is really secant squared of 2x dx. Okay. And now I do have integral of secant x. I have secant squared x. I have that. Because I think what function gives me the derivative of secant squared? That I can do. It's the 2x I need to worry about. So I do need to have a U-substitution for 2x. So du dx is equal to 2. So 1/2 of du is equal to dx. Go ahead and plug in. The 1/2 comes on the outside. Integral secant 2 secant squared u du. And then what I do is I say, well, yes, what function when I take the derivative gives me secant squared? Tangent. So this is 1/2 of tangent u plus c. And again, the plus c, when I multiply everything out, just going to be 1/2 tangent. The u is going to be 2x. The c is still c. And there I am. The next part is, okay, I need to worry about c. Oh my gosh. Cosine cubed. So now we're going to be a little tricky. So the way we're a little tricky is I say, well, I can rewrite this as cosine squared x times cosine x dx. I can go even further, and you should know that, hey, back last year you should have known that, hey, sine squared x plus cosine squared x is equal to 1. So that means I can replace my cosine squared x with a 1 minus sine squared x times a cosine x dx. But now what? And again, this is where it just takes practice and seeing things and trying to figure it out. And you have to be like, well, if I let u be cosine, my derivative is going to be negative sine. That's really not going to help me out because I have this 1 minus sine squared. Oh, I can let u be sine squared, and then when I take the derivative it gets messy. So in trying to be as simple as I can come over and say, well, let u equal just sine x. And now so when I do that, du dx is equal to cosine x. Oh, this is nice and clean because this comes out as du is equal to cosine x dx right there. So now what I have is now just the integral of 1 minus u squared du. And now when I take the antiderivative, I now have u minus u cubed divided by 3 plus a c. Substitute back in for my u. So I'm going to have a sine x minus 1/3 sine cubed of x. Again, just mind-blowing. This is incredible stuff. Okay, that you're able to, use all the tools that you've been given over the past to solve something so complex. Okay? Here we go. Let's see what's next. Okay, so this one here says evaluate using integral by substitution, definite integral. So we're saying, you know, obviously I can use substitution also on a definite integral. It doesn't just have to be on these indefinite integrals. So again, hopefully now that you started some practice, well, what can I do? Well, as far as to choose my u. So I'll let you think about it. See if you get it at the same time I do. What should I choose? If you said tangent x, that is correct. Because when I take the derivative with respect to x, I get secant squared x. In other words, du is equal to secant squared x dx, which means I can supplement or substitute that whole thing in there. Now what's completely amazing about this is now I can, when I substitute in, it's now the integral of u du. But what about those limits of integration? These limits of integration were in terms of x. And here's what's kind of cool. If I want to, since I put everything in terms of u, I can go ahead and now put my limits of integration in terms of u. Well, how do I do that? I substitute in. I can say, well, with the 0, I can say, well, that particular one is going to be tangent of 0, which is equal to 0. So this 0 comes down here, right there. And then I do tangent of pi over 3, which is then equal to square root of 3. I come over here. I try to give you some thinking time. Square root of 3. And that goes there. Now everything's completely in terms of u. Now I can, since everything's in terms of u, I can just solve it. And now when I solve this, well, what's the antiderivative? Well, the antiderivative is u squared divided by 2. Which is then equal to, evaluated from 0 to square root of 3. And when I do this, this then will be equal to three halves minus 0, which is just equal to 3 halves. Ow! Are you serious? This complex function right here, you found the area underneath the curve from 0 to pi over 3 for tangent x secant squared x. That's a complex function, and you found out that that integral, okay, that area between the x-axis and all the axis there and all that good stuff is 3 halves precisely. Psh! Mind-blowing. But that's how you do it. You put everything in terms of u, it becomes so much easier. Okay? There are other ways to do it, but it gets messy. 3 halves. Boom. There's your answer. Okay? One last example. This is going to be talking about the natural log. Okay, again. So hopefully we're getting in the groove of things. We're starting feeling out here what we're actually, trying to choose for u. I'm going to give you guys a moment of thinking time here. See what would you pick for u. Did you choose x squared minus 4? I hope so. Because when I take the derivative with respect to x, this is going to be 2x minus 0. Ooh. And when I solve for, set this dy, du is equal to 2x dx. Hey, look, once again I'm close. There's the x dx. There's x dx. So I divide both sides by 2. And then when I substitute in, now I have the integral. And 1 over u du. Notice again, I paused. I didn't put my limits to integration yet. I want to take care of that now. Oops, I forgot about the 1/2. Put my limits of integration in there. Oh, I plug 0 in there. So first one is 0 squared minus 4. Well, it's equal to -4. And that goes there. And then I do the 1 squared minus 4, which is equal to a -3, which goes here. And then always when you do this, the one check you want to do is, hey, do I have the smaller number on the bottom and the larger number on top? Because if not, you're going to have to flip them and take the negative. But in this case, we're good. Everything adds up, the smallest number's on the bottom. So now I go ahead and take the derivative, or antiderivative. When I do that, I start thinking, okay, so what function when I take the derivative gives me 1 over u? Again, hopefully, in your head, natural log of u. Notice the absolute values. They have to be there. Have to. Repeat that again. Have to. So I'm going to evaluate this from -4 to -3. And I go ahead and put my absolute, put my numbers in there. It should technically be this, right? So it's 1/2 natural log of 3 minus natural log of 4. And that's a happy answer there. You could be great with that. But if you remember your log rules, this is 1/2 the natural log of 3/4. And if you want to go take it to one step further, this is the natural log of 3/4 raised to the 1/2 power. Either answer would get you credit, all three of them. All right, there's some craziness that's going on in there, I know, but we're going to go ahead and give you your assignment. And here you go. You guys take care. We'll see you next time. And don't forget the quiz is coming up for this one after 7.1. Okay, so you get a little bit of a breather, but keep up with the homework. This is really hard. All right, talk to you guys later.